Okay, before we start with material today, so everybody, we're going to get going now, so please wrap up your conversations. Before we get going with today's material, just a couple of quick announcements. So 2 weeks from yesterday, the first exam starts, in case you've forgotten or been blissfully unaware of that. And so that means I believe the sign up in CASA should be available. I don't have any control over when that happens, so I'm not 100% sure that that's the case, but usually 2 weeks before it'll open up. So grab your preferred time slot, join the Hunger Games to get those last few, and make sure you show up at the correct time, make sure you have a reservation, double check that in case there's any problems. And then related to that, we're gonna have our first exam review. So the exam reviews will always be Fridays before the exam starts. And they're optional, of course. You don't have to come, and they will be recorded and put on YouTube, so you can watch it that way too if you prefer. And so if I have the dates right in my head, that should be February 18th. I'll remind you about this more than once, but just if you like to make a schedule ahead of time. The first one is February 18th. They're all going to be again, Fridays, same time, 2 to 4 p.m. Shouldn't be a full 2 hours, but that's what we allot just in case there's a lot of questions. And that's going to be in the classroom SEC 102. So that's closer where we usually have this class, in that SEC building close to mine. So that's going to be the first one, and I said every Friday before the exams start. So all 3 midterms and the final exam, we'll have a review session Friday at that time in that same room. So that's going to be the first one, and what I'll do for that is by the end of this week, I'll post it's sort of like a mock exam, full-length 20-question mock exam that we'll go through during that session. So you're encouraged to do that in advance if you can, or if you want to follow along while I do it, that's also okay, but it'll be available to you about a week before the exam reviews, and you can look at that ahead of time and bring it with you. All right, so that's that. And then if you were planning to come to office hours today right after class, which at this point in the semester is about 3 of you so far, but maybe more will take advantage eventually. I just wanted to warn you that as of 15 minutes ago when I left, all 3 elevators in my building are broken, so we have 0 working elevators. So if you want to come to office hours today, I'll be there, but you'll have to get a workout in before you can come see me, climb 5 flights of stairs. Hopefully they'll fix it in the next hour, but we never know. Okay, so that's that. So today is Tuesday, so as part of the 1 hour per day guarantees, it's our Try Hard Tuesday that we're going to go over some things related to study habits and progress in the course and how to keep up with everything. So the first thing I want to look at is sort of some results from the first 2 homework assignments. So we've had 2 so far that have come in. So we'll see if we look at the average scores for 2 of them. Chapter 1 homework was very good, 11.4 out of 12. We got a bit lower on Chapter 2 homework A, which is not surprising. Breaking news, Chapter 2 is harder than Chapter 1, as you all found out. So I'm not too concerned about the scores. They line up pretty well with previous semesters. And again, it's not the number of points we get on the homework that's important, is how much we learn from them. So what I am encouraged to see, although I still want to see further improvement, is how the number of attempts, I forgot to write this one in, the number of attempts has gone up. So on the first homework assignment, each student on average did 2.93 homework attempts, which again, we have a maximum of 4, and I encourage you to always do that. That's the number one thing you can do to keep up. And we had an average of less than 3 per student, and only about half of you, 61 out of 120, did all 4. So I sent a friendly, hopefully encouraging email to those that didn't do that, and encourage them to pick up their effort. And we did see some upswing, so we went up to 3.20 attempts per student, so about a 10% increase in the number of attempts we were doing, and about a 10 or 20% increase in the number of students who were doing all 4. So there's still about 50 people in the class who are not doing all 4 attempts on the homework. They're probably the 50 people that aren't here right now, but nonetheless, if you're in that category, I encourage you to step up your effort. It only takes maybe 2 hours a week or so to do those 4 attempts, and that's the best way to get the practice problems in on all the recent topics. So the next homework assignment is also on Chapter 2. It will focus a lot on periodic trends, things like atomic radius and ionization energy and electron affinity, things that we covered towards the end of last week. So you'll get another chance on Chapter 2 to review some of the important topics. But today we are going to continue on with Chapter 3 material. And so what we did in Chapter 2 is we talked all about the atom, the structure of the atom, how the electrons are arranged, the different theories for how those electrons behave in atoms, and so on. And now we're going to start talking about what really is chemistry, which is when 2 or more atoms come together to make a chemical bond, to make compounds. And there's 2 major types of bonding that we're going to talk about in this chapter. There's one more that we'll cover at the very end of the course. But the 2 major types of bonding are ionic bonding and covalent bonding. For ionic bonding, which we're going to cover here first very briefly, we don't expect you to know anything beyond the very basic concepts. We used to have a big long section on ionic bonding and all the energetics of that. So if you go through any of the older course materials, you might see things about lattice energy and Born-Haber cycle. We've pretty much eliminated that from the course. We kicked it down to chapter 7, and now I think it's gone altogether, so you won't even see that. So for ionic compounds, we just expect you to know the very basics, which is that when you have, as we learned last time, when you have metals on the periodic table, those elements on the left side, they tend to lose electrons to form cations, and they achieve the noble gas configuration by doing that. Nonmetals on the right side of the periodic table, they gain electrons to form anions, and when those two come together, cations and anions, you make ionic compounds, which are held together by ionic bonds. In an ionic bond, there's no sharing of electrons, it's purely just a charge-charge interaction, a positive charge and negative charge sticking together in what we call an electrostatic type of interaction. So what we should be able to do, though, is predict the formulas of ionic compounds. That's one thing we're going to ask you to do in this chapter, and then later on we'll tell you how to name ionic compounds. But again, the details of the bonding you don't need to know much. Just know that it's cations and anions sticking together by electrostatic forces. But when we're predicting the formula of an ionic compound, the charges must be balanced. So again, we're going to have both anions and cations, but we need to have the correct number of each such that the net charge is 0. All right, so there's no net positive or negative charge in an ionic compound. The charges have to totally balance out or cancel each other. So as an easy example, let's go to the periodic table quickly, and let's look at sodium and chlorine. So, close that. So sodium is Na right here. And as we said last time, that's in the first column. That's an alkali metal, so it will lose 1 electron to become a +1 cation in a stable configuration. And then chlorine over here is a non-metal halogen. It will gain 1 electron to achieve the configuration of argon. So sodium would form a +1 cation, chlorine would form a -1 anion. So when we write those out, if we have sodium plus and Cl minus, we just need 1 of each to balance the charge. The positive charge and the negative charge will cancel out when there's 1 of each, and so those two would form, as you guys are already familiar with, NaCl, which we colloquially refer to as salt. Okay, so that's how you predict the formula of a very simple ionic compound. You first predict the charges of the ions using what we learned last time, and then you make sure those charges balanced. Now, an important thing about writing the formula for an ionic compound is we want, for the subscripts, which tell us how many of each atom we have, how many of each ion we have in this case, we want the smallest whole numbers possible for the subscripts. So for NaCl, technically that's Na1Cl1. If the subscript is 1, we just don't write it. It's implied. So again, that's the correct way to write it, NaCl. Now there are many other combinations of sodium cations and chloride anions that would give you that charge balance. So if we had 2 of each, that would be balanced as well, 2 +1 cations and 2 -1 anions. Or if we had 3 of each, those would be balanced. But that's not the correct way to write the formula. So that's not how we're going to write these. I'll cross them out. We always want to write them with the smallest possible whole numbers, which in this case is 1 of each. So you have to make sure you divide by the greatest common factor if you want to use that mathematical terminology. Now let's go on to some slightly more complex examples. So if we have calcium 2 plus and O2 minus on the periodic table, we would again predict that those are the charges formed by those elements when they become cations and anions. Calcium is in the second column, oxygen is in the third to last column, so it would gain 2 electrons. So I'm not going to go through that again. But if we want to predict the formula of the compound, again, the charges have to balance out. So a sort of shortcut method for doing this, makes the math maybe a little bit easier in some cases, although the math is never going to be that complicated because the charges are basically going to be +1 to +3 or -1 to -3. You're rarely going to have anything outside of that. But what we can do is we can write the charges, and then what you do is you take each charge in absolute value and cross it over as the subscript of the other element. So this 2 plus becomes a subscript 2 on oxygen, that 2 minus becomes a subscript 2 on calcium. So you would come up with this formula. But again, we want to write it in lowest whole number ratios. 2 to 2 can be simplified to 1 to 1. So this would again be a 1 to 1 ionic compound CaO, one calcium, one oxygen. So that's a shortcut way of writing the subscript, of taking the charges and turning them into subscripts, but you just have to remember to reduce the formula if it's possible. And then an even more complex example where now the charges are not equal in magnitude. So if we have calcium and nitrogen, calcium again is a 2+ cation, nitrogen forms a 3- anion based on its location on the periodic table. And we can do the same trick. We can take the charges and cross them over and make them the subscript on the other element. So the 2 from calcium becomes a subscript of 2 on nitrogen, the 3 on nitrogen becomes a subscript of 3 on calcium, and that gives us this formula here, Ca3N2, which cannot be reduced any further. It's a 3:2 ratio. If you try to reduce that, you're going to get fractions. We never want to have fractions or decimals as our subscripts in any sort of chemical formula. All right, so that's going to be the correct formula for the compound that forms from calcium and nitrogen. And again, to check out that the charges balance out, what we have in this formula is 3 calciums, each with a +2 charge. So you have a total of +6 from calcium. For nitrogen, we have 2 of them in the formula, and each of them, as we said, is 3-. So that's a -6 charge from nitrogen, so those are equal and opposite. They cancel each other out, +6, -6. You can always check yourself afterwards to make sure that the charges balance out. So for ionic compounds, for now, that's all we need to worry about. As I said, later in this chapter, we'll learn how to state the name of an ionic compound, but in terms of predicting the formulas, that's really all there is to it. We'll add in a little bit of complication later on, too, with what are called polyatomic ions, but for now, this is all we need to know. What we're going to spend most of today talking about, and really most of I would say this chapter and the next chapter, chapters 3 and 4, are going to be covalent bonds. So in a covalent bond, 2 electrons are shared between 2 atoms. So this is the difference between covalent and ionic. In ionic bonds, one atom loses electrons, the other atom gains electrons. They're not sharing those electrons, they're just held together electrostatically. In a covalent bonds, 2 electrons are shared between 2 atoms. So that's the key difference of a covalent bond versus an ionic bond. So if we look at this diagram here, sort of shows you what happens when 2 atoms come together to form a covalent bond, where they're basically the 2 atoms approach each other and eventually they get close enough together that an electron from one atom and an electron from another atom, they can overlap in the same region of space, and the 2 atoms will then share those electrons. And so this is an energy diagram. So we're not going to go through this in a lot of detail in this course, but it's helpful to understand it a little bit. So the y-axis is potential energy, or just energy in more general terms. And again, we're using the convention that we've been using since the Bohr model, which is that when opposite charges attract each other, the energy is negative, and when there's charges repelling each other, the energy is positive. And so when you bring 2 atoms together, we're starting here, it's from, on the right side is when the 2 atoms are really far apart from each other. So when they're really far apart, there's no interaction between the 2 atoms, and so the energy it approaches 0. As we start bringing the atoms together, what happens is that the electrons on one atom and the protons on the other atom, and vice versa, the electrons from the second atom and the protons from the first, start attracting each other. So you get new attractions between the protons in the nucleus and the electrons that are now being shared, and so the energy decreases and you get this dip in energy to negative values. So again, the energy being defined as negative because in this regime, the attractive forces are winning out. But then what happens here is it starts to go up as you try to bring the atoms too close together, because what happens when you bring them too close together is that 2 things. First, you're forcing the electrons to be in a really close space to each other, so the electron-electron repulsions start dominating, and also at the limiting extreme, the 2 nuclei get really close together, and the 2 nuclei start repelling each other. So as you bring them too close together, those repulsive interactions win out, the energy goes back up and eventually is positive if you bring them too close together. So this minimum point here is sort of where those 2 atoms will be, and so the distance between them we'll define as the bond length or the bond distance. We're going to define that clearly here in a second. And the energy of this interaction, this negative energy, is going to be the negative of the bond energy. So this negative of the bond energy is defined as positive, and this is the bond length or bond distance there. So that minimum point, you read it down to the x-axis and the y-axis, that gives you these 2 properties. So let's define these 2 properties in a little bit more detail now. So bond energy is also known as bond strength. It has a few different names. They all mean really the same thing. bond strength, or bond association energy, if it's being more precise. So those are a couple different ways of saying the same thing, but what it refers to is the energy required to break a bond. Now we're going to use a word here that we haven't fully introduced yet, which is mole, is coming, and it will be a big part of the course later on, but it's the energy required to break 1 mole of a bond in the gas phase. So a mole is just a huge collection, so it's not a single bond that you're breaking a whole bunch of them, and you're reporting the energy for that. A mole is kind of like a dozen, but it's a much bigger number than a dozen. So that's why they're going to be defined in energy per mole, but don't worry about that for now too much. It's just how much energy is required to break a bond. And so it's defined as this. If we have 2 atoms bonded to each other, A and B, in the gas phase, the bond energy is described as the energy that's required to separate them into the individual atoms A and B. And so this change in energy for this is called the bond energy for A and B. And it's always a positive number. It says how much energy is required to pull the 2 atoms apart. Remember, the atoms are forming a net attraction between them by sharing those electrons. So we have to put energy in to rip those 2 atoms apart, so it's always a positive number. It means that we have to put energy into the system. All right, but that's what's defined as bond energy, is how much energy is required to break a bond, and how it refers to then how strong that bond is, how strongly the 2 atoms are held together. And the other one, which is called bond length or bond distance, is the distance between the nuclei of 2 bonded atoms. So this is kind of how they determined atomic radius. It's related to atomic radius, but now it's the distance between the 2 nuclei of atoms that are bonded to each other. So if we have A and B bonded to each other, and let's assume that they're 2 different sizes, although if they're 2 different atoms, they will be. So this is our AB, these are the 2 nuclei. This distance here between the nuclei, that's going to be our bond distance. All right? Or a bond length, I guess is how I abbreviated it before. So I'll call it BL for bond length. Okay, so that's the distance between the 2 nuclei of 2 atoms that are bonded to each other. And a key concept that we need to understand as we make predictions about the properties of bonds, because one thing you'll be doing on the Chapter 3 homework is we'll be giving you a bunch of bonds to compare, and we'll ask you, which one is longer, which one is stronger, and you have to make predictions about that. And a key concept is that bond distance is inversely related to bond energy. So in general, if the bond is longer, it's weaker, and if the bond is shorter, it's stronger. And that sort of makes sense, right? Because if we bring the 2 atoms closer together, we're going to have the electrons that are shared being closer on average to the 2 nuclei, which is going to cause a stronger attraction between them. So the closer the 2 atoms are in a bond, the stronger they're held together. So there's sort of that inverse relationship between these 2 properties. So that's going to be key for understanding how the 2 relate to each other and making predictions about them. So that's how we define the 2 basic properties of a covalent bond that we're going to focus on, and we'll just to sort of and then move on to this. We have another property here called bond order that we're also going to consider. So bond order is the number of bonding pairs between 2 atoms. So as I said, at minimum, a covalent bond requires that we have 2 shared electrons, but in many cases we can share more than 2 electrons. They're going to be typically shared in pairs. So the number of shared electron pairs is what we call the bond order. And there's really only 3 that we're going to consider in this course, because we're only going to be doing this for main group elements, which are limited to either single bond, double bond, or triple bond. So for a single bond, that means the bond order is 1, which means there's 1 shared electron pair between the 2 atoms. We'll learn a little bit later how to predict bond orders for simple molecules, but for now, let's just take the example of hydrogen bonded to itself. That's going to be a bond order of 1. And there's 2 ways of writing this. So when we want to sort of indicate that we have 2 atoms bonded together with a bond order of 1, if we write the two atoms with a single line between them, that single line means that there's a single bond, two shared electrons. Or you'll sometimes see it written more explicitly with each dot representing an electron. So again, there's two electrons shared between the two atoms, indicating a bond order of 1. So that would be what we call a single bond. A double bond would be a bond order of 2. That means we have 2 shared electron pairs, or a total of 4 electrons that are shared between the two atoms. And an example of a simple molecule that forms a double bond is oxygen, O2. And we write that either with 2 lines between the two atoms, indicating 2 bonds or 2 shared pairs, or again, we can write them explicitly. This is not as common, but you'll see this in some sources, where we write out the electrons individually as little dots, and now in this case for a double bond, you would need 4 dots indicating the 2 shared electron pairs. And then taking it one step further, the highest bond order that we'll consider in this class, although you can go higher if you go to the transition metals, but that's not a topic for this course. But for main group metals, the highest bond order you'll see is 3. And just following the same pattern, that means you have 3 bonding pairs. So nitrogen forms a bond order of 3 with itself, so it would be written as 3 lines indicating 3 bonds, or again as 3 pairs of dots, which gets a little bit unwieldy, but that's an alternative notation for this. And the key point about bond order, which we're going to talk about in a little bit more detail here in a second, is again, what we're going to ask you to do in this section of the course is predict properties of bonds relative to each other. And an important point is that the higher the bond order, it sort of correlates with those other 2 properties that we just talked about. So if the bond order is higher, that makes the bond shorter because you have more shared electrons, so the atoms are being pulled together more strongly by those shared electrons if there's more of them, and that also means then the bond is stronger. All right, so the higher your bond order, the shorter the bond is, and the stronger the bond is. So those are all 3 now related to each other in that way. All right, so that's the third major property of a covalent bond. There's actually one more that we're going to get to today as well, but that these 3 are all closely related to each other, so it's important to understand that relationship. So just to reiterate this now once more, let's talk about trends in bond length. So as I said, this is a typical type of question you'll see on the Chapter 3 homework, not until next week still, so you have a while to internalize this, but where we'll give you, again, a few different bonds like I'm doing here and asking you to predict which one is stronger, which one is shorter, which one is whatever, and so on. So when you're comparing bond properties, either bond length or bond strength, which have that inverse relationship to each other, the first thing you want to look at is the bond order. Okay, so bond order has a huge effect on bond length. If you increase the bond order, you're going to make the bond much, much shorter. So it's a much stronger, and also on bond strength, so they both go together. So especially if the atoms you're comparing are all in the same part of the periodic table, meaning the atoms themselves are all similar in size. So for this series here, we have CF, C double bond O, C triple bond N. All of those are P block elements, all really close to each other on the periodic table, so the atoms themselves are all kind of similar in size. So if you want to compare the bond lengths of these, because they're all different bond order, that's what we're going to use as our most important criterion. So we look for, if we want to find the shortest bond, that's going to be the one that has the highest bond order. So we would expect C triple bond N to be the shortest, the double bond next, which has in the middle, and then the single bond last. So if you're comparing bonds that have different bond orders, focus on the bond order first. That's going to be the most important thing to look at when you're trying to decide if a bond is shorter or a bond is stronger. That's the most important and the most impactful of those properties. The second one to look at, though, if you have bonds that are all the same order, so if we're asking you to compare a bunch of single bonds or more than one bond that has the same bond order, then you're going to look at the size of the atoms involved. So we learned last week at some point, how to predict the relative atomic radius using the periodic table. And so basically, if the two atoms that are bonded to each other have a larger atomic radius, that's going to correlate with forming a longer bond. Because in some sense, the bond length is the sum of the two atomic radii. It's not quite as simple as that, but it's related. So if you have two big atoms bonded together, they're going to have a long bond length. The two nuclei are going to be far apart. If you have two small atoms bonded together, they can get closer, and they're going to have a shorter bond length. So those two concepts are also closely related. So if we're predicting the properties of these three bonds and comparing their bond lengths, CF, CCl, SiCl, they're all single bonds in this case, so we can't use bond order to look like us. We have to look at the size of the atoms involved. So what's helpful is to look at comparing two bonds at a time and comparing them where they share one of the atoms. So these first two both have carbon in them. So let's figure out which is smaller, fluorine or chlorine. So we go to the periodic table. Fluorine F is there, chlorine Cl is there. As you go down a column, the atoms get larger, so Cl is larger than F. So when carbon is bonded to chlorine, which is larger, we would expect that bond to be longer than the bond when carbon is bonded to fluorine, where it's smaller. Again, the smaller the atom that is bonded to, the closer together they can get. So comparing these two, Cf is going to be smaller than CCl in terms of bond length, because again, the fluorine atom is smaller than chlorine, so it can get closer to carbon and form a shorter bond. And then if we look at the other one, SiCl, CCl and SiCl both have chlorine in them, so if we just look at the relative sizes of carbon and silicon, we can make a prediction about the relative bond lengths of CCl and SiCl. So on the periodic table, again, we find carbon and silicon. Silicon, again, is below carbon in the same column, so silicon is larger than carbon, which means the bond that it forms with chlorine will be longer than the bond that carbon forms with chlorine. All right, again, it's sort of like the sum of the two atomic radii. They both have chlorine, but silicon is larger, so when we compare those, you'd expect silicon chlorine to be longer because it has a larger silicon atom compared to carbon. So ranking all three of them then would be in this order here. All right, so again, you have to sometimes use the size of the atoms, going back to the atomic radius trends we learned last time, to figure out how large the bond, relatively speaking, how long the bond is when all the bond orders are the same. All right, so any questions on that before we move on to the next major topic? All right, so the next topic we're going to cover is another property of atoms called electronegativity. So this is the last periodic trend we have. So we learned periodic trends last week for atomic radius, which we just reviewed, for ionization energy, and for electron affinity. And now the fourth one we're going to have is called electronegativity. Now electronegativity is a property of an atom when it's bonded to another atom. So it doesn't really make sense to talk about the electronegativity of a single atom, but when you have two atoms bonded together, the electronegativity of the two atoms in that bond can have some important effects on the properties of that bond. So electronegativity, let's define it first. It's the relative ability of a bonded atom to attract shared electrons. So what we're the concept we're developing now is that when two atoms share two electrons in a covalent bond, they don't necessarily share them equally with each other. All right, so the sharing is not always 100% equal. So as an analogy to this, so I have an identical twin brother. So when we were growing up, we shared a room. That was forced upon us. But we were pretty much, we're the same size, same strength, same relative toughness and tenacity. So the room was pretty much shared exactly equally. He had half the room, I had half the room, and it worked out pretty well. But if you have a much older brother sharing a room with a much littler brother, then the sharing might not be so equal. The bigger brother is going to claim more of the space. And in the same way, when two atoms are bonded to each other, sometimes one atom claims more of the electrons than the other one. They don't share them perfectly equally. And so that's the concept that electronegativity will allow us to understand. It's the relative ability of an atom in a bond to attract those shared electrons to itself. So again, the shared electrons are not necessarily shared equally. So there's a scale for electronegativity, a numerical and unitless scale. So it's a relative scale, so these numbers don't have units associated with them. And there's a few different electronegativity scales, but the one that's most commonly used was derived by a scientist named Linus Pauling, who's shown above. Spent most of his career at Caltech in California. And so it's, again, a relative scale that it's not a particularly precise scale. It doesn't cover a huge range of numbers, so it's not something we can sort of split with a fine-tooth comb, but nonetheless, there's some important trends that are associated with this. So the highest electronegativity on the periodic table is fluorine, which has an electronegativity on the Pauling scale of 4.0. Now, you don't want to remember too many of these numbers, but there are some helpful benchmark numbers, and remembering that fluorine is 4.0 is somewhat helpful, and also remembering that it's the highest is going to be important for things that we do. And the lowest electronegativity values are in the opposite corner of the periodic table. So fluorine's on the top right. If we go to the bottom left, that's where the lowest electronegativity values are. So cesium and francium, which are in that bottom left corner, they have electronegativities of about 0.7. So as you can see, it's not a huge range of numbers, but that's kind of the range that we have. And you don't really need to know about how this was defined. You know, where do these numbers come from? What do they mean? We're not going to go into all the details, but basically what we did, what Pauling did, was he looked at the bond energy of different, different types of bonds with two atoms bonded to each other, all these different combinations of A and B, and so the ideal bond energy for A and B bonded together would be 1/2 is basically the average of the two, AA bond and BB bond. So if it was a perfectly covalent bond between A and B, the bond energy would be equal to this, where you take the bond energy of A with itself, the bond energy of B with itself, and average them, and if the electrons are shared perfectly between A and B, then that's the number you would get. But in reality, that's not true for most bonds, and so when that happens, that means the electronegativity is different, and so by comparing the actual bond energy to this idealized value, that's sort of how he ended up developing this scale. I'm leaving out a lot of details to that, but that's what he did, was measuring bond energies. So it's related to bond energy, but again, we don't have to know exactly how these numbers came about. But that's what they are, and they relate to, again, the ability of an atom to attract electrons when they're shared with another atom. So the relative trend for electronegativity is, as we go across a period, again, that's going to be from left to right across a period, the electronegativity increases. So we're going to write here the trend for increasing electronegativity. As we go down a group, the atoms become larger, so the shared electrons will be further away from their nucleus, so that means the electronegativity decreases. They have less of a pull for those shared electrons. So then the increasing trend would be bottom to top. And so basically it's the same trend as electron affinity, which is a closely related parameter for atoms. Now we need to understand the difference between electron affinity and electronegativity. They're not the same thing. So remember that electron affinity is the property of an individual atom and is how much it wants to gain an extra electron to form a negatively charged anion. So again, that's just a single atom forming a negative ion. Electronegativity is a property of an atom when it's bonded to another atom and how strongly it pulls those shared electrons to itself. So they're a little bit different, but they are related to each other. So typically atoms that have high electron affinities also have high electronegativity, and so that's the trend that you find. And really there's no major exceptions to this trend. So unlike electron affinity and ionization energy, where we had to worry about, group 2 and group 5 have either abnormally high or abnormally low values, for electronegativity we don't have to worry about that. Because when two atoms are sharing electrons in a bond, their individual electron configuration doesn't matter anymore, and so the trend is very smooth as you go bottom, top, left to right. There's very few places where you would see a decrease in electronegativity as you move in these directions. Does that answer your question? You had a question, but I want to make sure I don't skip it. Yes, so there would also be an inverse trend between electronegativity and atomic radius, which, as I sort of already said, and the reason for that is because if the atom is smaller, it tends to be able to pull the electrons to itself better because the nucleus will be, closer to the shared electrons. So they are related in that way, and so yeah, the trends, the periodic trends are kind of all intertwined in some level. But electronegativity is the last one we're going to cover. This is how you would predict it. Now, the important part of electronegativity is what is sort of the consequence of electronegativity, and that comes into play with what we call bond polarity. All right, so again, this is the idea that electrons are not necessarily going to be shared equally when two atoms form a covalent bond. Sometimes one atom sort of hogs more of the electron density, and more of the electrons are going to be, on average, closer to that atom, and there's going to be an imbalance in the charge distribution. So bond polarity is a situation when atoms with different electronegativity values are bonded to each other. And when that happens, the bonding pairs of electrons, however many there are, whether it's a single bond, triple bond, or double bond, whatever shared pairs of electrons you have are going to be shared unequally in this case. So anytime the electronegativity between the two atoms is different, there's going to be an unequal sharing. Okay? So let's talk about how we sort of indicate polar bonds and talk about what it means to be polar. So if you have hydrogen and fluorine bonded to each other, a simple molecule HF. So when atoms with different electronegativities form a bond, they're going to have unequal sharing of electrons. So if you have H and F, the electronegativity for hydrogen is going to be 2.1, and electronegativity for fluorine is 4.0, as we said. So clearly there's a difference in electronegativity between hydrogen and fluorine. And one way to indicate this is with a vector. Now, because physics is not really a prerequisite for this course, some of you may not be comfortable with the idea of vectors, so that's understandable. But you basically draw it in this way with the arrow pointing towards the more electronegative atoms. That's one way to indicate an unequal sharing of electron density, where again, the arrow points to the more electronegative atom, which means that has more electron density or more negative charge is going to be concentrated near the fluorine atom. So that's one way to indicate a polar bond, with the arrow pointing towards the more electronegative atom. The other way, which I think is more common, especially for this course, is going to be if we have an HF bond, again, same story, but the more common way of indicating the polarity is going to be in this way. So again, the fluorine atom is more electronegative, which means it's going to hog the electron density relative to hydrogen. It's going to have more of the shared electrons near fluorine. So we put a delta minus there, lowercase delta in this case for you Greek letter aficionados. So we put a delta minus near the more electronegative atom and a delta positive by the other one. Again, indicating that there's an imbalance in electron density where the electrons are not perfectly shared, but they're going to be closer on average to fluorine. There's going to be more negative charge over here. It's not a full negative charge. It's not the same thing as an ionic bond where the fluorine is completely -1 and the hydrogen atom is completely +1. The electrons are still shared, but they're just not shared equally. So that's how we indicate it with a delta minus and a delta plus. So we put that delta minus, which is a partial negative charge, not a full negative charge, on the more electronegative atom. All right, so that's two ways of indicating that a bond is polar. And you might see, probably especially the second one here, you might see that in some of the homework assignments. And then what the, so how do we then decide how polar a bond is? Is it just a little bit polar? Is it very polar? How do we sort of rank that and categorize that? That's going to come from the difference in electronegativity between the two atoms. So if we know the electronegativity of the two atoms in the bond, the difference between them is going to determine how polar that bond is. So we call that delta En is one way to abbreviate it. So if we have two atoms bonded to each other, A and B, delta En is just the absolute value of the difference between the electronegativity of A and the electronegativity of B. All right, again, we're just taking the two electronegativity values and subtracting them. Now, there's not really a quantitative meaning to that necessarily, but we can kind of set up some general dividing lines between different delta En values and what that means about the type of bond that we have. So a perfectly covalent bond, that means the electrons are shared perfectly equally between the two atoms, is going to happen when there's no electronegativity difference, when delta En equals 0. So if you have two atoms with the same electronegativity bonded to each other, they will share the electrons perfectly equally, and you'll have what's called a perfectly covalent bond. Now, this is rigorously only true if it's the same atom bonded to itself. But again, the electronegativity scale is not very precise, so there are some atoms that are different from each other that still have essentially identical electronegativity values. if we went to really high precision, that would not exactly be true, but there's some that are very close to each other, so those would form bonds that are pretty much perfectly covalent.
What's that thing again, like rigorously what?
Rigorously true when the same atom is bonded to itself. And when that is true, we say that the bond is nonpolar. So when you have a perfectly covalent bond or a bond where the electronegativities are the same for the two atoms, we say that that bond is nonpolar. So if you have, for example, hydrogen bonded to itself in H2, or chlorine bonded to itself in Cl2, oxygen, O2, etc. So if it's the same atom bonded to itself, it's going to be perfectly covalent and nonpolar. But again, it's sometimes possible for two different atoms to be bonded together where the electronegativity value is essentially identical, and you would still classify that as a nonpolar bond. So carbon and sulfur, if you just round to one decimal place, they both have electronegativity values of 2.6, so a bond between carbon and sulfur would be pretty much nonpolar. Again, not perfectly so because they're two different atoms, but to a good approximation, nonpolar. But if you have a significant difference in electronegativity between the two atoms, then that's when you get into the continuum of polar or ionic bonding. So there's no set cutoff for this, but if your delta En value is greater than 0, meaning that the two are different, and smaller than about 2, we typically would call this a polar covalent bond. Now, the real way to tell if it's a polar covalent bond versus ionic is typically for a polar covalent bond, we're talking about two nonmetal atoms bonded to each other that just happen to have different electronegativity values, but they can be fairly different from each other. Like we saw for H and F on the previous slide, their difference in electronegativity is about 1.9. So that's still a covalent bond because it's two nonmetals and the difference is not huge, but it's a pretty polar bond because the electronegativity values are different for those two. If the difference in electronegativity is greater than 2, that's typically going to be what we would classify as an ionic bond. But usually an ionic bond is, the more rigorous way of defining it is metal and a nonmetal bonded together. So if a metal and a nonmetal bond together, they tend to form ionic bonds where, again, the metal loses electrons, the nonmetal gains electrons, and those two typically have very large electronegativity differences because metals have small electronegativities and nonmetals have large electronegativities. But there's really all possibilities in between those extremes of perfectly covalent and ionic. And the key thing we want you to understand is that there's no real cutoff for polar covalent versus ionic bonding. It's not like they're two different things. Really, there's a continuum of bonding between the two extremes of perfectly covalent and ionic. So even though we often, for simplicity, classify them as either covalent or ionic, there's not really a set cutoff between covalent and ionic. They're all one in the same. It's just how big the difference in electronegativity is determines if it behaves more like a covalent bond or more like an ionic bond. So what you would say then is that some of the way we describe this is if you have a larger difference in electronegativity, we would say that that bond is more polar or has a higher percent ionic character. So those are kind of two ways of saying the same thing. All right, so in the limit of really large electronegativity difference, you have a high percentage of ionic character and the bond is like an ionic bond. And then there's, in the limit of no electronegativity difference, it's completely nonpolar and it's a perfect covalent bond, and everything in between is possible. So it's a continuum. There's not really a cutoff between ionic and covalent, but it's all determined by that difference in electronegativity, whether you would classify it as perfectly covalent, polar covalent, or more as an ionic bond. That's kind of what's determining that. All right, so any questions on electronegativity values? All right, so the next thing we're going to cover with this chapter, and I hope to God this is still in your book because I forgot to check if they cut this out. So we have a new version of the book this year, and I'm not a very good student, so I don't read the book as often as I should. And so I think this is still in there. I really hope it is. I guess I'll double check that after class, but it doesn't hurt to learn it anyway. It's useful. All right, so what we're going to do is really in this chapter, probably, I don't want to jinx myself, I think this is the only numerical type of problem you'll have in this entire chapter. So this chapter 3 is all about bonding and all about, structures of compounds and naming compounds and things like that. So it's a whole lot of conceptual stuff. This is the only numerical thing that I can think of for this whole chapter. And it's using bond strengths to calculate delta E for a reaction. Now we're kind of jumping the gun a little bit here because we haven't even talked about chemical reactions, and the whole concept of a change in energy for a reaction is going to be a foreign concept to us. But at this point we can say that whenever substances react with each other, where two elements react to form a compound, or two different compounds react to form new compounds, whenever that happens, there's going to be an energy change for the reaction. It's either going to absorb energy from the surroundings or release energy, usually in the form of heat. So you'll see that later on in the course in more detail. So delta E is the change in internal energy when reactants convert to products. All right. So what we can do to estimate delta E for a reaction is use the bond strengths in all the reactants and all the products. So essentially, the reactants and products are not going to have identical bond strengths because you're rearranging some of the bonds whenever you do a chemical reaction. And so that's what is responsible for this change in energy, because the bond energy that's holding those atoms together, it's going to get released when new bonds form. You have to put energy in to break the new bonds, and if those two energies are not the same in the reactants and products, there's going to be some change in energy for that whole process. So here's sort of the strategy we'll take, where we can, if we know the bond strengths for everything on the reactant side and everything on the product side, we can use those values to estimate delta E. So first we break all the bonds in the reactants, which requires energy to input. So that step has a positive delta E. We have to break all of the bonds in the reactant side, and we use the sum of all their bond energies to figure out how much energy that takes. And when we write out chemical equations, which we haven't covered in detail yet, the reactants refers to the left side of the equation, on the left side of the arrow. And then what we do, we've put all the energy in to break all the bonds on the reactant side, and then they all get scrambled up and form new bonds in the products, and we're going to calculate how much energy is released when the new bonds form. So we look at which bonds are present on the other side, the product side, and that is going to, a different quantity of energy is going to be released when all those new bonds form on the product side. And this time we're forming bonds, so the energy is going to be released, or delta E for that side is going to be negative. So we have negative delta E on the product side because we're forming a bunch of bonds, which releases energy. So however many products you have, they're all going to have different types of bonds in them. And so we look at which bonds are present in the products, either one product or more than one product, whatever the situation is, and we figure out how much energy is released when all those bonds formed. And then the overall delta E for the reaction is going to be, this is the Greek letter sigma, which means sum. If you've taken, I'm sure you've seen this in math classes before. So we sum up the bond energies on the reactant side, which will all be positive numbers. And then we subtract from that the sum of all the bond energies on the product side. All right, so it's reactants minus products, where again this sigma means the sum, and bond energy is abbreviated as BE in this equation. All right, so bond energy is the same as we defined it earlier. Now we're going to use the numerical values given to us for reactants and products and sum them up and subtract them from each other to get delta E for the whole reaction. You have a question in the back? Yes, so we will take account, we're going to do an example problem. You have to take into account how many of each bond there is, because the bond energy value you're given is going to be how much energy it requires to break one of those bonds. But if there's more than one of that bond, either because the reactant or product has more than one bond in it, or because there's more than one reactant and product forming and reacting with each other, because of coefficients that are present, then you have to account for that and multiply the bond energy you're given by how many of that bond you have. So that's the other step that we have to keep in mind, which we'll see when we do this example. So we're just going to do one example of this, which I'll do for you since it's the only example. So let's look at this reaction here. We take this compound here is called formaldehyde. You may have heard of it. And we react it with phosphine, which is a horribly nasty and dangerous chemical. Don't work with this if anyone asks you to. And then we react those two together and we form this product here, where we've drawn out, again, so when you're doing these problems, you need to account for how many of each bond you have, and you need to account for the bond order in some cases. Because as we'll see here, on the reactant side we have carbon-oxygen double bond. On the product side we have carbon-oxygen single bond. We're given values for both of those, which are different from each other because the double bond is much stronger. So let's make sure we also account for the correct bond order when we're doing these problems as well. So what we're going to do is we're going to sum up all the bond energies on the reactant side first. All right, so on the reactant side we go to this first reactant here, and we have one CH bond and another CH bond, so two bonds between carbon and hydrogen. So there's two of those, and the bond energy for CH is given as 413 kilojoules per mole. We'll just write it as kilojoules because it's 2 moles times 413 kilojoules per mole, so we get 826 kilojoules to break those two CH bonds. We have one bond between carbon and oxygen in this, but it's a double bond as shown here with 2 lines. So let's make sure we use the correct number for carbon-oxygen double bond, which is 745. So there's one carbon-oxygen double bond. And then in this here we have pH3, which we didn't draw the whole structure out, but it's phosphorus with 3 hydrogens. Hydrogen always forms single bonds. That's something we're going to see later on. So pH3 would look something like this with 3 single bonds to hydrogen. Anytime you see H2, H3, whatever, that means each of them is bonded to that other atom with single bonds. So pH is 320, but there's 3 of them. So we have 3 pH bonds. Each one is 320. And so we get 960 for those. So when we add all of those up, the sum of the bond energies on the reactant side. So these types of problems are more like accounting than chemistry. It's just keeping track of numbers and making sure we don't forget anything. So that's the sum of the bond energy on the reactant side. That's half of the piece of the puzzle. And now we have to do the same thing for the product side. We only have one product that has a bunch of different types of bonds in it, so we have to make sure that we accurately account for all of those. So on the product side, I'm not going to be able to show both pages at the same time, unfortunately, very easily, so we'll flip back and forth. So with this product, we have 2 CH bonds still, carbon, hydrogen, carbon, hydrogen. So we kept those 2 CH bonds, we didn't change that. So that's the same number that we use for CH above. 2 times 413 is 826. We have a bond between carbon and oxygen in this product now, but now it's a carbon-oxygen single bond. It went from a double bond to a single bond. So we're going to use that value there for carbon-oxygen single bond, which is 358. So on the product side, we have a carbon-oxygen single bond now, which is 358 kilojoules. And then we have over here, it doesn't matter what order we put these in, but we have an OH bond. That's a new type of bond that we have. OH is given here as 467 kilojoules. So you'll typically be given all the numbers you need unless we're asking you to solve for just a single unknown. So there's no way to calculate these or memorize these numbers. They're going to be given to you when you need them. So that's 467 kilojoules for the OH bond. And then there's 2 more bonds left. So we have a carbon-phosphorus bond there. CP bond is 264. So 1 CP bond with a 264 kilojoule bond energy. And then finally, the last type of bond we have is pH. We still have pH bonds, but this time we only have 2 of them. We had 3 in the reactant side, now we have 2 on the product side. So we're going to use that number for pH bonds and just multiply it by 2 this time. So that's going to be 320. So that's 640. So adding up all 5 of these numbers now, that's going to give us the sum of the bond energies on the product side. Which is 2555 kilojoules. And then finally, the delta E, which is what we're asking for here, is going to be the sum of the bond energies from the reactants, which we calculated above, minus what we just calculated, which is the sum of the bond energies on the product side. So reactants minus products in this case, based on how bond energy is defined. So that number was 2,531 kilojoules, determined on the previous slide. We just got 2555 for that one. And that's going to be minus 24 kilojoules. All right, and not to belittle our friends in the Bauer School, but I think that's about as difficult as any accounting problem will be, just keep track of all numbers like that. Okay, so that's what we get for that. That's how we would do it. Now, the one thing that this problem doesn't show that you should be aware of is sometimes the reactions have coefficients. So if we react hydrogen with oxygen to make water, it can be written in this way. So we have to also account for the coefficients out front, which tells us we have 2 H2 molecules. So even though H2 just has one HH bond, there's 2 of them, so we would still need to double the value for that. And then similarly in water, which has, you know, this sort of structure here, 2 OH single bonds, but there's 2 of them now, so it's a total of 2 times 2, which is 4. So make sure you also account for coefficients. This reaction didn't have any coefficients, so we didn't have to worry about that. We just had to count them up based on the structures that we were given. But in some cases, the coefficients are also present in the reaction, telling you how many hydrogen or water molecules or whatever else is reacting. And you have to account for that also when totaling up the number of bonds that you have. So that'll be one that you'll hopefully see on the homework assignment. I should double check to make sure our book didn't drop that topic, because I forgot to check that today before class, but it should be there. And if it is there, that's really the level of depth you need to understand it in. All right? All right, any questions on that one? All right, the last topic we're going to cover today and continue on next time are called Lewis structures. And this is a fairly important topic in this course because it's going to be presented as in chapter 3 as we're going to start covering it now. But in order to do everything we're going to do in chapter 4, you also have to be able to draw good Lewis structures. So this is a topic that's going to transcend at least 2 different chapters in this course, if not more than that. So you have to make sure we learn this well. So a Lewis structure is a 2-dimensional representation of a covalent molecule. So again, covalent molecules are ones that have typically only nonmetals as part of their structure. And a Lewis structure shows us a 2-dimensional representation of a molecule. So it doesn't give us the precise shape necessarily, as we're going to cover in the next chapter. But what it does is it shows all of the valence electrons in the molecule. All right, so we've drawn some very simple structures already that just show 2 atoms bonding to each other. That would be in some sense a Lewis structure, although in that case we left out some of the valence electrons. So the Lewis structure has to show all the valence electrons, and we're going to learn how to do it for things that are a little bit more complicated than just 2 atoms bonded together. All right, so in a Lewis structure, each atom is represented by its atomic symbol, so that's pretty straightforward, and we've already seen that in the depictions that I gave for individual bonds with 2 atoms bonded together. So you can have more than 2 atoms bonded together, and each atom is going to be represented by its atomic symbol. So there should be no surprises there. But as I said, the Lewis structure shows all of the valence electrons for all the atoms in the structure, and they're going to be shown in 2 ways, either as bonding pairs or as lone pairs. So as we've already talked about for bonding pairs, they're going to be shown as solid lines, where each line represents a shared pair of electrons between 2 atoms. And we can have single, double, or triple bonds, which would indicate those bonding pairs with 1, 2, or 3 lines. All that is the same. But the other thing that a Lewis structure shows is what are called lone pairs or non-bonding pairs. So when atoms come together to make molecules, not all of the electrons are going to be involved necessarily in forming bonds. There's going to be some that remain non-bonding, which are going to be shown as dots. And these are going to be localized on a single atom in the structure. These are electrons that are not shared between 2 or more atoms. They're going to be electrons that are localized on one atom in the structure and not involved in forming bonds. All right, so that's the key thing of a lone pair or non-bonding pair. These are valence electrons that are not involved in bonding. and they're localized on one atom in the structure. So what we're going to do for the, yes, sorry, before I move on. So the significance of lone pairs is that, so basically, each atom is going to bring, as well, this will make more sense as we go through this process. Each atom brings a certain number of valence electrons with it based on where it is on the periodic table. And the electrons that are not being shared with other atoms still have to be there. They don't go away, or else you're going to have positive charges everywhere. So those extra electrons are going to be localized around that atom and not involved in bonding with another atom, but they're still going to be there. They have to be shown to have a complete and correct Lewis structure. Now, in this course, we're not going to talk too much about the significance of those non-bonding electrons, but if you take organic chemistry after this, which many of you will, those non-bonding electrons are very important in organic chemistry because they're often involved in reactions with other substances. So a lot of times, not always, but a lot of times when two substances come together and form a new substance by forming new chemical bonds, the electrons that were originally non-bonding in the reactant side end up being involved in forming the bond on the product side. So knowing how many non-bonding electrons there are, which atoms are located on, can help you predict how two things will react with each other. Now that's way beyond the scope of this course, but that's why they're important, and a correct Lewis structure will show them. The other thing that non-bonding electrons are important for, which we will cover in the next chapter, is they help determine the shape of the molecule as well. So you can't forget about them, because if you're going to predict the shape of the molecule, you do need to know how many non-bonding electron pairs there are, specifically on the central atom in the structure. So they're important for that in that way too, which we will see in this course. All right, so that's why they're important, and what we're going to learn now is, again, we'll continue it next time. We probably won't finish this today, but we're going to learn a step-by-step process for figuring out where all of the valence electrons go in a Lewis structure. So where the bonding electrons go, where the non-bonding electrons go, counting them up, making sure that they're all shown correctly. Okay? So step one in drawing a Lewis structure is to find how many valence electrons there are, because the final structure that you have needs to have the correct number of valence electrons based on what atoms are in the formula. So what we do is we add up the total for each atom. So we learned in the previous chapter how to figure out how many valence electrons there are, and that's based on the location on the periodic table. We're only going to be doing this for non-metals, so it's going to be fairly straightforward, just based on which column in the periodic table it's in. We use that to figure out how many valence electrons there are. And we have to remember to account for the number of each atom, because each atom is going to bring its own set of valence electrons, and if there's more than one of that atom, each of those atoms is going to have the number of valence electrons that it's going to contribute to the full molecule. So you have to account for the number of each atom in the chemical formula. So for example, if we have CO2, we have to account for the fact that there's two oxygens. So when we're counting valence electrons, we have to add up the valence electrons for two oxygen atoms, not just one. And then there's some simple one. The simplest one to keep in mind that you don't even really have to do any work on is hydrogen. All right, so if we have hydrogen in our formula, which many of these will, it's going to contribute one valence electron only. And the other key thing about hydrogen when we draw Lewis structures is that it always forms one single bond, and that's it. Never going to have multiple bonds to hydrogen, never going to have lone pairs around hydrogen. You just draw a single bond to hydrogen and whatever else is in there and you're done. All right, so if I see you guys, I don't usually see you guys drawing Lewis structures because all the homework is on Blackboard, but if I see you guys drawing a Lewis structure that has either double bond to hydrogen or lone pairs on hydrogen, every time that happens, a small piece of me dies, so don't do it. That's the number one rule. Okay, so don't let that happen. So hydrogen is the easy one. But if we're doing any other element besides hydrogen, which is, it's usually going to be p block elements, but sometimes we can do s block elements for this as well. But as we talked about, the number of valence electrons for those is going to be the outer ns plus np electrons, which in the way that our periodic table is numbered corresponds to the group number. Again, this is for the highest n value you have, the outermost electrons. But we already talked about that before, so we're going to count the valence electrons the exact same way. And based on the group number in the periodic table for those main group elements, that gives us directly how many valence electrons there are. So group 1, which is the first column, 1 valence electron. Group 2, which is the second column, 2 valence electrons. Group 3, which is the first column of the p block, that's 3, and then the rest of the p block, 4, 5, 6, 7, 8, and so on. So counting valence electrons will become second nature the more we do it. Now the other thing you have to account for, though, is if there's any charges in the molecule. So we're not only going to do this for neutral molecules, we might also do it for what are called polyatomic ions, which are groups of covalently bonded atoms that have a net positive or negative charge. So if we have a negative charge in the polyatomic ion, we're going to add additional electrons to account for each negative charge. And if we have a positively charged polyatomic ion, which is not as common but can happen, we're going to subtract electrons for each positive charge. So we add them up for each atom based on where they are in the periodic table, but again, there can sometimes be extra electrons that would be allow us to make an anion or too few electrons, which makes a cation. We have to make sure we account for that as well. So we'll see an example of that today as we go through. So we're going to go through all these different steps now for 3 different molecules, which show us some different features of Lewis structures, I think. So that's why I chose these 3. So we have PCl3, NO3-, and IF5. So let's determine the number of valence electrons for each of them. That's always going to be step 1 for a Lewis structure. So for PCl3, we have phosphorus and chlorine, are the 2 elements. And if we go to the periodic table and find the electron configuration for phosphorus and chlorine, they're close to each other. So both of them would have a core electrons represented by neon. Phosphorus is going to be 3s2, 3p1, 2, 3. So that's a review of chapter 2. Chlorine is going to be 3s2 and then 3p1, 2, 3, 4, 5. So that's the electron configuration for each of those. If we want to write that out in full, they don't need to do this every time, as we'll see. So phosphorus is 3s2, 3p3. Chlorine is 3s2, 3p5. So the total valence electrons for phosphorus is going to be 2 plus 3, which is 5. We count the s and the p electrons in the outermost shell. And then for chlorine, 2 plus 5 is 7. And so then the total would be, we have to account for how many atoms we have. We have 1 phosphorus, which contributes 5 valence electrons. We have 3 chlorines, Cl3 in the formula, so that's going to be 3 times 7 for each, so that's 26 total electrons. All right, so that's one way to find valence electrons. You can go through and write out the configuration and pick out the valence electrons, but that's a little bit laborious. The easier way, as I'll show you in this next example, is just to use the group number on the periodic table. All right, so for NO3-, we have nitrogen and oxygen are the two elements. So if we go to the periodic table and just look at the group numbers, again, we're using Roman numerals here. So this is 1, 2, 3, 4. Stop. Come on, don't crap out on me now. All right, so nitrogen is here in group 5A, so that means it contributes 5 valence electrons. Oxygen is right next to it in group 6A, so it contributes 6. So the group number for these A groups, that as are notated in our periodic table, that directly gives you the number of valence electrons. So group 5 is 5, group 6 is 6. And so then what we have is nitrogen, we have 1 in the formula. So that's 5 valence electrons from nitrogen. For oxygen, there's 3, but each of them contributes 6 because they're in group 6. That's another 18. But then the other thing we have to account for is this overall negative charge that's shown in the formula. This is what's called the nitrate anion, as we'll learn later. So we have to add 1 more electron to account for the negative charge. Okay, so we can't forget about charges if they're there. So we have 5 plus 18 is 23 from the atoms, plus 1 more from the negative charge, a total of 24 electrons. And then for IF5, we have iodine and fluorine. And if we find their location on the periodic table, this is group 7A. Fluorine is also group 7A, so we have 2 different group 7 elements. So each one is going to contribute 7 valence electrons. Those valence electrons are in different subshells, but there's still a total of 7 for each. So 1 iodine contributes 7, and then 5 fluorines, IF5, each also contributes 7. So that gives us a total of 42. All right. So again, this will become second nature the more you do it, but that's always the key first step for a Lewis structure, is to make sure you know how many valence electrons you're working with. Because as we go through and draw the structure, we have to make sure that we're using all of those valence electrons in the final Lewis structure that we produce. We can't have more than this, or we can't have less than this when we have that final Lewis structure. All right, so that's step 1, counting the electrons. Step 2 is going to be to start drawing the structure. Now you might develop your own method for this. I don't think you have to follow my step-by-step approach, and as you practice it, it'll become, as I said, easier and more routine. You can start skipping or sort of combining steps together. But the next thing to do is to start drawing the structure, and you do that by putting the least electronegative atom in the center and draw single bonds to the other atoms. Now in 99% of the cases, it's very obvious which atom goes in the center because you have PCl3, 1 phosphorus, 3 chlorines. I think the phosphorus should go in the center and be surrounded by chlorines. Or NO3, 1 nitrogen, 3 oxygens. IF5. So usually the atom that's by itself that you have one of, that's going to be your central atom. In cases where it's not obvious, sometimes we'll indicate to you what the central atom should be if it's important. Or as I said, when in doubt, put the least electronegative atom in the center. That's usually what happens. But in this case, it's pretty obvious. We're going to put PCl3 phosphorus in the center. And the next step is going to be just start by drawing single bonds to all the other atoms in the structure. All right, this is only step 2 out of 5 or so, so this is not going to give us there. But we also have to then count for how many electrons we have left. So in PCl3, we found that there was a total of 26 valence electrons. By drawing 3 single bonds, each single bond is 2 electrons, remember, each bond is 2 electrons, so 2, 4, 6. We've used up 6 of our 26 electrons. So we still have 20 electrons to figure out what to do with, so we're not anywhere close to done yet, but that's going to be step 1, is just starting with single bonds. NO3 minus, we do the same thing. NO3 minus has 24 valence electrons, as we just determined. Those 3 single bonds contribute 6, 2 for each bond, so there's still 18 left, so we have to figure out what to do with the other 18 electrons. That's going to be subsequent steps, and then same for IF5. I in the middle, single bonds to all 5 fluorine atoms. And then this structure had 42 valence electrons. Each of these 5 single bonds contributes 2, so there's a total of 10 from those bonds that we've drawn in, and there's going to be 32 electrons left to figure out with. So the next steps in these are going to be figure out what to do with the rest of these additional electrons that aren't accounted for in the bonds that we've drawn already. So that's step 2. That's very simple, sort of mindless second step to do this. And then moving on to the next step, what we're going to do is the rest of these electrons we're going to distribute as lone pairs. So every other atom is going to be added to the structure as a non-bonding or as a lone pair. So the first thing we do is we do what's called completing the octet of the outer atoms. So there's this thing called the octet rule. It's violated a lot, so it's not a rule that is always important, but generally for the outer atoms this is going to be followed. So the outer atoms are going to follow the octet rule. And after we draw that first single bond, we're going to complete that octet by using lone pairs. And so what the octet rule refers to is that in just about every case for these types of Lewis structures, when you have p-block elements, the total number of bonding and non-bonding electrons around an atom is going to equal 8. All right, so in a Lewis structure, and that octet rule is always going to be followed for the outer atoms unless it's hydrogen. So again, hydrogen does not follow the octet rule. Don't try to do it for hydrogen. You're going to have to put a bunch of lone pairs on and lead to my early demise by doing so. So for those, you don't want to do it, but for any of the p-block elements that are on the outside, oxygen, fluorine, chlorine, like we have in these structures, you want to have 8 electrons around the outer atoms in particular. So that's what we're going to do first. We're going to complete the octets of the outer atoms. Then if we still have leftover electrons, those are going to go now on the central atom as lone pairs. So we always complete the octets of the outer atoms first, and then we add the remaining electrons to the central atom. All right. Now one thing to keep in mind is for the central atom, if the atomic number is greater than 10, meaning we're in the 3rd row of the periodic table or below, it is possible to expand the octet of the central atom, meaning the central atom can have more than 8 electrons. So you can go beyond 8 electrons in the central atom if it's in the 3rd row of the periodic table or below. If the central atom, though, or any atom in the structure is smaller than atomic number of 10, meaning it's in the first 2 rows, they can never exceed the octet rule. All right, so those are some important things about the octet rule to keep in mind. It's not always going to be followed, especially for the central atom, but it depends on what the central atom is, whether it's possible to go more than 8 electrons. Another key point is that if you're going to expand the octet rule in any of the atoms, if any of the atoms in the structure are going to have more than 8 electrons, it has to be the central atom. All right, I don't like to use the word never, but I can not think of a structure that has a greater than octet on the outer atoms. So it's only going to be the central atom that will expand its octet. And there's 2 elements that typically will have incomplete octets as a central atom. So beryllium, which is technically a metal, but you might see Lewis structures involving beryllium, and boron, which is the next one over. They typically have incomplete octets when they're the central atom. So those are called electron deficient. So those are some key situations where the octet rule will be violated. If you need to put lone pairs on the central atom, you can do that, and you can go beyond 8 electrons if the central atom is in the 3rd row of the periodic table. And beryllium and boron will typically have less than 8 electrons. So let's follow this step then for the Lewis structures we've been building up, where we distribute the remaining electrons as lone pairs. So for PCl3, we started with this. We use 6 electrons for the bonds. That leaves 20 electrons to distribute as lone pairs. All right, so the first thing we do is we complete the octets on all of the outer atoms, which are chlorine. Right now, each chlorine has a single bond to phosphorus. That bond is 2 electrons for that chlorine. So we have to add 6 more to each chlorine. 1, 2, 3, 4, 5, 6, 3 pairs. We complete the octet of chlorine. So chlorine now has 2 electrons from the bond, 4, 6, 8 electrons from the non-bonding electrons. And we do that for each and every one. So now we have a total of 24 electrons in the structure, because each chlorine now has 8, it's a complete octet. We need to have 26 total, so those last 2 are going to go on the central atom. So again, we put the lone pairs in the central atom last. So this accounts for all 26 electrons that we need in the form of bonding and non-bonding electrons. For NO3-, we had 24 valence electrons, and we used 6 of those again in single bonds. So we have 18 left to put on as lone pairs. So we're going to complete the octets of the outer atoms first. We need 6 more on each outer atom to give it a total of 8. So that's all 24, because we've added 8 to each oxygen, 2 in the form of the bond, 6 in the form of the lone pairs. 3 times 8 is 24. That's how many total electrons we have. So in this case, we do not have any lone pairs left for the central atom. All 24 electrons now are arranged around the outer atoms. And then finally, for IF5, we have 42 total electrons. We drew in those 5 single bonds earlier. So that was 10 of our electrons. That means we have 32 left to put around the central atom. Or sorry, as non-bonding pairs first on the outer atom, so that's 6 for each fluorine to complete their octets. All right, so what we have now is 5 fluorines, each with a complete octet, so 5 times 8 is 40. So that's 40 of our 42 electrons, so we have 2 electrons left. Now they must go in the central atom. So the last 2 again, when we have extra, go in the central atom. So again, only after we've completed the octets of the outer atoms do we put any remaining on the central atom. So we had 32 electrons left, 30 of them went as lone pairs on fluorine, the other 2 went here on the central atom. All right, so that's step 3, and then let's stop here because this one gets a little bit more confusing. So I'll push this off to next time, and we'll cover that next time and finish off these Lewis structures. So it turns out that we'll see next time that these 2 are completely done already. We don't have to do anything else to those. We'll check them. We'll do some checks on them, but they're done. But we still have a couple more steps left for nitrate to finalize its structure, NO3-. So we'll get to that next time, and we'll do a couple of practice examples before moving on to some new topics related to this. All right, I'll see you guys on Thursday.